this lecture, I want to talk about native tokens and how they are supported by Plutus, how you can use Plutus to define a so-called minting policy to determine under which conditions native tokens can be minted and also burned. But before I get to that, I have to explain what value means in Cardano. When I talked about the extended UTXO model, I explained that each UTXO, each unspent transaction output, has an address and a value. And then when that was extended to the extended UTXO model, additionally, a UTXO also has a datum. And we have seen examples of such datums in previous lectures. But in almost all the examples we have seen so far, the value was always simply an ADA value or Loveless value. An exception was the first contract I showed you as an example, namely the auction contract. Because in that example, the item that was auctioned away was an NFT. So this NFT was also a value which was not ADA. But we just created this NFT out of thin air in the playground. So we just used this playground feature that makes it possible to start with other native tokens other than ADA that are already in existence. In the real Cardano blockchain, however, in the beginning, there are only ADA. There are no other native tokens apart from ADA. So you have to do something to create new native tokens or to burn existing ones. And in this lecture, we'll see how to do that. But let's first talk about values. The relevant types are defined in package Plutus-Ledger-API, and the modules of interest are plutus.v1.ledger.value, and then special support for ADA in plutus.v1.ledger.ada. Let's look at the value module first. A value is defined as a map from currency symbols to maps from token names to integers, which sounds a bit weird and complicated. So the first thing to note is that each native token, including ADA, is identified by two pieces of data, a currency symbol and a token name. And if we go to the top of the module, we see that a currency symbol is just a new type wrapper around a byte string. And the same is true for token name. Token name is also just a new type wrapper around byte string. So we have these two byte strings that identify a coin, or it's also called an asset class. We have this new type asset class, which is a wrapper around a pair consisting of a currency symbol and a token name. So ADA or Loveless will be one asset class, and custom native tokens will be other asset classes. And this map from currency symbol to map token names to integers is equivalent to a map from asset classes to integers, which means that a value just says how many units of each asset class are contained in it. Let's start the REPL and let's import the two relevant modules, Plutus v1 ledger value and Plutus v1 ledger ADA. Let's also activate the overloaded string extension so that we can enter byte strings as literal strings. Incidentally, both currency symbol and token name also implement the isString class. That means we can enter both of those as literal strings as well. Now let's look at some values. Let's start with Loveless values. In the ledger.ada module, there is a function called ADA symbol, and this is of type currency symbol, and that gives us, not surprisingly, the currency symbol of the ADA asset class, and that's just the empty byte string. And there's similarly a function ADA token, which will give us the token name, and that is also the empty byte string. So taking both symbol, currency symbol, and token name as the empty byte string gives us ADA or Loveless. And so how do we construct a value containing just Loveless? We have seen that before in the examples. There's a function Loveless value of that, given an integer, gives us a value. So for example, to have 123 Loveless, we can just do this and we get a value. And by the way, you would never construct a value directly by constructing these maps. Instead, there are always helper functions you can use, one of those being Loveless value of. So here we see this map. So the outer map, the map where the keys are currency symbols, has one key, and we don't really see it here. That's because the currency symbol of ADA is just empty currency symbol. Okay, and the value is now a map from token names to integers, and we see this inner map here again has just one key, the empty string. That's the token name of Loveless. And finally, the value is 123. So this value represents 123 Loveless. One thing we can do with values is we can combine them, add them. So in the case of Loveless, so let's take another example. Loveless value, I don't know, 10. And how do we combine them? Well, it turns out that the value class is an instance of monoid. We briefly mentioned monoids in the last lecture when we talked about the writer monad. So monoids are things that you can combine that have a neutral element called mempty, and you can combine two elements to a third element with mapend. But there's also an operator for that that's written like this. That comes from semigroup, which is a superclass of monoid. So doing something like this, I can combine two values. So having the value that represents 123 Loveless and the value representing 10 Loveless, I get a value with 133 Loveless. So how do we create values containing native tokens? There's a very useful function called singleton. And it's a function that takes three arguments: a currency symbol, a token name, and an integer. And that will construct a value consisting of just one asset class given by the currency symbol and the token name, and the integer specifies the amount, how many coins of that asset class are there. So we can construct a value with the native token by now first giving a currency symbol, and as I mentioned before, because we have the overloaded string extension activated, I can just give the currency symbol as a literal string. However, that can't be an arbitrary string. It must be a string representing a hexadecimal value for reasons I'll explain in a minute. So for example, we can do something like A8FF, just as an example. So next comes the token name. That can be an arbitrary byte string. And I can just do whatever, for example, ABC. And now I must give the amount, how many coins, let's say 7. And I indeed get a value. Now we see that in the outer map, the map where the keys are currency symbols, I have one entry, my A8FF, and then the value is an inner map given in this case only the one token name ABC and the amount 7. Now of course I can also combine as before with this mapend operator. So for example, I can take this and combine it with Loveless value of 42. And let's say I can combine it with another singleton, maybe using the same currency symbol, A8FF, but a different token name. 100. Let's see. So now we get a somewhat more interesting map. So now in the outer map, we have two keys. One has the empty currency symbol, so that's for the Loveless, and then a second entry that has the A8FF currency symbol. In the Loveless case, the inner map, there's only the one token name, the Loveless token name with the value 42. But in the A8FF currency, in the inner map there, we have two entries for the two token names we now have, ABC and XYZ, with amounts 7 and 100 respectively. Let's give this value a name. Let's call it V. And another useful function is, given a value, to extract the amount for a given asset class. That is called value of, and it takes a value and a currency symbol and a token name and gives us the corresponding amount. So if we try that with our V, value of V, and take currency symbol A8FF and as token name, for example, XYZ, then we get the 100 back. If we take ABC, the 7. And if we take a token name that's not contained in the value, ABC lowercase, we get 0. Another useful function is flatten value. That takes a value and returns a list of triples, currency symbol, token name, integer. So as the name suggests, it flattens this this map of maps into a flat list of triples. So if we apply this to our example value V, we just get a list with 3 entries. The first two are these native tokens, both with the same currency symbol but different token names. And the last entry here is the Loveless, the 42 Loveless. Now the question, of course, is why? Why do we both need a currency symbol and a token name? Why don't we just use one identifier for an asset class? And why does the currency symbol have to be built from hexadecimal digits and can't be an arbitrary string? And this is where so-called minting policies come in. So the rule is that in general, a transaction can't create or delete tokens. So everything that goes in also comes out. The exception is the fees. So there's always a fee in Loveless that has to be paid for each transaction. Right now, at the moment, that's a flat rate of 10 Loveless, but that will soon change and then depend on the size of the transaction and the amount of steps that the validation scripts take to execute and the memory consumption of the validation scripts. So, but if that was the whole story, then of course we could never create native tokens. And this is where minting policies come in and where the relevance of the currency symbol comes in. So the reason that the currency symbol, the byte string giving the currency symbol, has to consist of hexadecimal numbers is that that is actually the hash of a script. And this script is called the minting policy. And if we have a transaction where we want to create native tokens or burn them, then for each native token that we try to create or burn, the currency symbol is looked up. That's the hash of a script. So the corresponding script must also be contained in the transaction, and that script is executed along with the other validation scripts. And similar to the validation scripts that we have seen so far that validate inputs, the purpose of these minting scripts is to decide whether this transaction has the right to mint or burn tokens. And Ada actually also fits into this scheme because remember the currency symbol of Ada is just an empty string, which is not the hash of any script. So there is no script that hashes to the empty script. So there is no script that would allow the minting or burning of Ada, which means that Ada can never mint it or burned. All the Ada that exists come from the Genesis block, the Genesis transaction, the very first transaction, and the total amount of ADA in the system is fixed. It can never change. So only these custom native tokens can have custom minting policies and can be created and burned under certain conditions. So we'll look at an example of a minting policy next and see how it works and see that it's very similar to validation scripts but not identical. Before we write our first monetary policy, our first minting policy, let's briefly recall how validation worked that we have seen so far. So when we don't have a public key address, but a script address and a UTXO that sits at such a script address and a transaction that tries to consume that UTXO as an input, then for each such script input, the corresponding script is run, the validation script. And that validation script as input gets the datum, which comes from the UTXO, the redeemer, which comes from the input, and the context. And here we can see the context again. Recall that's in package Plutus minus ledger minus API as well in the module plutus.v1.ledger.context. And so it's defined here. And it has two fields, the txinfo field and the script purpose field. And we saw that for script purpose, everything we have seen until now always had the purpose spending txoutref, where txoutref is a reference to the UTXO we try to consume. And this txinfo has all the context information about the transaction that is being validated. Now for monetary policies, for minting policies, this is triggered if the txforge field, in this one here, txinfo forge, of the transaction contains a non-zero value. In all the examples we've seen so far, this was always zero, which means in the transactions we've seen so far, we never created or destroyed tokens. But if this is non-zero, so we have a value here, then this value, as we have seen just now, can contain a bag of asset classes, so different asset classes for different currency symbols and different token names. So if this is non-zero, then for each currency symbol contained in this value that is being forged, the corresponding minting policy script is run. So each currency symbol is the hash of a script, of a policy script, a minting policy script. And for each value that appears here, for each currency symbol that appears in this value in the forge field of the transaction, the corresponding script that belongs to the currency symbol is executed. And where the validation scripts had three inputs, the datum, the redeemer, and the context, these minting policy scripts only get one input, only the context. It's the same context as we had before, but there is no datum and no redeemer. That wouldn't make sense because a datum belongs to a UTXO and a redeemer belongs to an input, but this forging belongs to the transaction itself, not to a specific input or output. So the only input that the policy script gets is the context. And as I just mentioned, there's this purpose and the info. And the purpose in the case of forging or burning of tokens will not be spending as we saw before, but will be minting. And minting with argument currency symbol we are looking at. So that could in principle be more than one if in this forge value there are more than one different currency symbols present. And for each of those, the corresponding policy script will be run. I created a new module called free, and let's write a very simple minting policy. When we wrote a validator, we always had a function that took at least the datum as argument, some datum type, whatever, D, and a redeemer, and then the script context, and returned a bool. We also saw the low-level version in the beginning where the first three arguments were all of the same type of datum, and instead of bool we had unit. But as I said, in practice we use this typed version. So there can also be optionally arguments in front of this if we have a parameterized script. We also can have parameterized policy scripts, and we'll see that as our next example. But first, let's look at one that's not parameterized. So if we instead want to do a policy script, let's call it make policy. And as I mentioned before, we don't have a data and we don't have a redeemer. So we just have this simple type. It just takes the script context and returns a Boolean. And let's write the simplest monetary policy, the simplest minting policy that we possibly can. And that would be the one that ignores the argument, ignores the context, and always returns true. So this is the minting policy that allows arbitrary forging and burning of tokens of the currency symbol that belongs to this policy. When we wrote validators after having defined the Haskell function that contains the logic, we needed to compile it to Plutus core to get an actually script instance. And something very similar we have to do now as well. So in order to get an actually policy, we can define something. So the type will be scripts monetary policy. And there's a function called make monetary policy script. And now we need to actually compile the function, and we use Plutus template Haskell as before. So Plutus TX compile, that's the same that we had before. And now again, we need the quote where we have to quote the function. But as before as well, the compile expects this low-level function where everything is datum and we don't have bool but unit. And in the case of validators, we use this wrap function to turn a typed function into this low-level function. And there's something for monetary policies as well. It's called wrap monetary policy. And as argument, it just takes the function make policy that we have defined. Okay. And now also, as in the case with validators, this wouldn't work because the make policy function is defined outside of these Oxford brackets. So as before, we have to add an inlineable pragma here. Finally, now that we have a policy, we can get a currency symbol from the currency. So let's call it cur symbol of type currency symbol. And there's a function script currency symbol that takes a policy and turns a policy into a currency symbol. So like this. I reload in the REPL, and now I can look at cur symbol and I get this hash. So we have a currency symbol. So this is the first currency symbol that we have defined. Now that we have our policy and our currency symbol, that completes the on-chain part. But in order to try it out and to interact with this, we also need a corresponding off-chain part. And what would this off-chain contract do? Well, it should allow arbitrary wallets to mint and burn tokens of this currency symbol. So what would be the input data that we need? Well, we have the currency symbol. So what's missing is the token name and the amount, the number of coins we want to mint or burn. And that motivates defining a data type mint params. That will be the parameters that our contract uses. And it has these two fields, a token name and an amount. So the idea is if the amount is positive, then executing the corresponding endpoint should create tokens of our currency symbol with this token name and the given amount. And if this amount is negative, then the tokens should be burnt. The next step is to define a schema. Remember, one of the parameters of the contract monad was the schema that defines the available actions that we can take. And as always, we have the blockchain actions that give us access to generic things like getting the current slot, getting your own public key, and so on. And then with this type level operator, we can define endpoints. In this case, we only need one endpoint. I call it mint, and it uses the parameters that are just defined. So now if we use this schema as a parameter to our contract type, then this endpoint will be available. So now we can look at the contract itself. I call it mint. So it takes the mint params that we just defined and returns a contract. And in the past, I never went into details with the off-chain contract, but after last lecture, now we know about the contract monad, so now I want to explain it in much more detail. So recall the contract monad takes 4 type parameters. The first one is the type of status that we tell that uses this writer monad feature of the contract monad. And by keeping this parametric with a small w, I basically indicate that I don't make use of this feature. So I won't tell any state in this contract. The next parameter is the schema that we just discussed. So by using free schema, I have the usual blockchain actions, plus I have access to the mint endpoint. The third parameter is the type of error messages. And as I said before, text is normally a good choice. Finally, the last parameter is the return type, and our contract won't have a return type, or will just have a unit return type. Okay, so I can define mint, MP are the mint parameters, and because contract is a monad, I can use do notation, which I do here. And the first thing I want to define is the value that I intend to forge. And I'm using the singleton function that we tried out in the REPL earlier. And recall the singleton function takes 3 parameters: the currency symbol, the token name, and the amount. And then it creates a value that contains just one entry, one asset class, given by the currency symbol, the token name, and then the amount. So the currency symbol is our currency symbol that we just defined. The token name we extract from the parameters. So we access the MP token name field of the MP value. And finally, the amount we also extract from the parameters. So we use the MP amount field of MP. So val now denotes the value we want to forge. I'll come to lookups in a second. Let's skip that for now. And let's look at this line first. So one of the main purposes of the contract monad is to construct and submit transactions. And the path that the Plutus team has taken to do that is to not explicitly define transactions. So, I mean, that would be the obvious option. We just define every single necessary field for a transaction. The fees, the forge field, all the inputs with redeemers and so on, all the outputs, give just a complete transaction in detail. But that would be very tedious, and there's lots of repetition there, because often if you need to make ADA payments, for example, you have to look into your wallet and find UTXOs in your wallet that you can spend to use for that. Or if you have change, or if you get money out of a contract, you by default want to pay it in your wallet. So these things happen over and over again, and therefore a different approach is used with these constraints. So the idea is that you declaratively define certain conditions that the transaction you want to construct should have. And then the Pluto's libraries automatically take care of constructing a transaction that fulfills all these conditions, if possible. And these conditions all have names that start with must. If you look at the previous examples, there are things like must spend script output, must pay to public key, and all sorts of conditions that you can put on a transaction. So in this case, we are only interested in a single condition, namely we want that the transaction we construct forges the value, this val value that we just defined. That's all we want. And then automatically, for example, it's not clear by just this condition where this newly forged value should go, but that will then automatically end up in our own wallet. So after defining these conditions, you use a function like submit_tx. There's a variety of similar functions. They're all called something like submit_tx and then something else. So in this case, the appropriate one is submit_tx constraints with. And these functions all take these conditions that we defined, these declarative conditions that our transaction should satisfy, and then they try to construct a transaction that fulfills these conditions. So in our case, the only condition is that we want to forge the value. So what must this function now do in order to turn this condition into a valid transaction? Well, it must, for example, balance it. So if inputs are needed or outputs are needed, it must add. In this case, for example, because we always have transaction fees that we have to pay for each transaction, we need an input that covers the transaction fees. So automatically this submit_tx constraints with will look up our own UTXOs and find one or more that are big enough to cover the transaction fees and use those UTXOs as input to the transaction that's being constructed. Furthermore, because we are forging value, let's first assume that the amount here, the MP amount, is positive. So we are actually forging newly minted token. That must go somewhere after we forge it in the transaction. So the submit_tx constraints with will, in the process of constructing a valid transaction, automatically generate an output for this transaction that sends the newly minted token to our own address, to our own wallet. If this amount was negative, it would be the other way around. So then these tokens are burned, so they must come from somewhere. So in that case, the submit_tx constraints with would automatically find an input in our own wallet to take these tokens from. And by the way, this function can also fail. For example, if we want to pay somebody but we don't have enough funds, so there are not enough UTXOs in our own wallet to cover the funds we want to spend in the transaction, it would fail. Or in this case, if we want to burn tokens, so if the amount is negative but we don't have the tokens that we want to burn in our wallet, this would also fail. So in that case, an exception would be thrown, and with an error message of type text. Now for these lookups. In order to fulfill these conditions here and to construct the transaction, sometimes the library needs additional information. So in this case, to construct a transaction that forges its value with this currency symbol, as I said before, in order to validate such a forging, the nodes that validate the transaction have to run the policy script. But the currency symbol is only the hash of the currency symbol of the policy script. So in order to run the policy script, it must actually be included in the transaction, which means that in this step, in this construction step of the transaction, when the algorithm sees this must forge value constraint, it knows it has to attach the corresponding policy script to the transaction, so that then later during validation, the script is found and can be executed. And in order to tell the algorithm where the script is, we can give it hints, and that's these so-called lookups. So there's also a variety of different lookups. You can give UTXOs, or you can give validator scripts, and you can also give monetary policy scripts. So in this case, all we have to give as an additional hint for the algorithm to solve this is this monetary policy, and then we specify the policy that we defined above. So the policy is the actual script, and the currency symbol is just the hash of the script. But in order to construct this transaction, we need the actual script. And we do that by using these lookups. And then in this submit TX constraints with, one of the arguments is the lookups. There are also variants without the with, where we don't need lookups. So in some of the previous examples we saw, we didn't need this lookup mechanism. We didn't need to pass in additional information. So we could use a different member of this family of submit TX. And finally, this add void. Well, most of these constraint functions are geared towards using a specific validator script. So normally you have this situation that you are working on a smart contract on one specific smart contract. So you will often deal with that specific smart contract. And that specific smart contract has a datum and a redeemer type. And all these functions, these constraint functions, or most of them, are parametric in the datum and redeemer type. And so you can then directly use this datum and redeemer type, and you don't first have to convert it into the Plutus datum type. But in this case, we are not making use of that. We don't have any validator script. So that means this submit TX constraints with wouldn't know which type for datum and redeemer to use, because we don't have any datum and redeemer types in this example. So in that case, we must somehow tell the compiler which type we use. And we don't care. I mean, there is no datum and redeemer, so we can use this void type that doesn't have a value. So that's like a little technical twist. Right, and we see that, I mean, these were just simple definitions with let, but here we actually use monadic bind. So this is actually a monadic action that's happening in the contract monad. And the reason for that is, as I mentioned, in order to construct this transaction, the algorithm, this function has to look up UTXOs in our own wallet, for example, to cover the transaction fees. So it must make use of these blockchain actions, of this superpower of the contract monad, that it has access to the UTXOs, for example. So this is a monadic action, and we bind the result, call it ledger TX. So this is now basically a handle on the transaction that we just submitted. So this submit TX doesn't just construct the transaction, it also submits it. Now I wait for it to be confirmed. That could go wrong. If something is wrong here, I mean, nothing should go wrong here. So we should only ever construct a valid transaction here. If something goes wrong, it could be because we don't have enough money to cover the fees, for example. In that case, as I mentioned before, we would just get an exception. But after submitting it, we wait for confirmation. And if for whatever reason this transaction actually was invalid, so we submitted, but then validation fails, this confirmation would never happen, and this line here would block forever. But this is only a temporary affair. Soon the Plutus team will make that more sophisticated, so that it's you can't just wait for confirmation. You can also listen to status changes. So, for example, you will be able to detect whether validation failed and things like that. But right now, I think this is good enough. So we just wait until it's confirmed. And then in the end, we make use of the fact that we have logging available in the contract monad, and we just log a message that we forged this value. Finally, we need some more boilerplate and define our actual endpoints. So this mint is just a function from mint params to a wallet contract. But in order to actually run that, for example, in the playground, we must do something more. So we define another contract, endpoints, and that's always the name of the contract that the playground will run. So if you want to test something in the playground, you always need something called endpoints. And so what do? we define a helper function min prime and then recursively call endpoints again. So that will make sure that the mint endpoint is always available. Once we've executed it, it will again be available. And this min prime, well, we somewhere must get the mint params. And for that, we use the endpoint function that I explained in the last lecture. So the endpoint function is a contract that just blocks until from the outside, in the case of the playground, that would be from the UI, somebody provides the parameters. So in this case, that will be of type min params. So this action here, this contract action, will block and wait until mint params are provided. And then I use the monadic bind to, after I have the mint params, call mint with those parameters as argument. So what this will do, it will block until mint params are entered, and then it will call the mint contract that we just defined. And because of this line here, after this is done, it will recursively call itself again. So it will block again until a new mint is triggered, and so on. And finally, this is just needed for the playground to provide the necessary UI in this line as well. Let's try this in the playground. So I give an initial supply of 1000 Lovelace for both wallets 1 and 2, and we see here the minting action is available. And I already defined a script. So I want to demonstrate that with this minting policy, every wallet can forge and burn the token. So I first call mint for wallet 1, and as token name I just arbitrarily picked ABC, and as amount just as arbitrary 555. And I also have wallet 2 mint the same token, so same currency symbol and same token name, the amount 444. Then I wait for one block to allow these transactions to take effect. And then I just want to demonstrate the burning. So wallet 1 now burns 222 of the tokens. Let's try that out. And here we see what's happening. So this, as always, is the Genesis transaction, which just gives 1000 Lovelace to both wallets. Now let's look at these two. That must be the ones where we actually mint tokens, and this will be the one where wallet 1 burns some tokens again. So let's look at this first. So that's incidentally the one from wallet 2. So we see this input is needed to cover the fees, and that has been automatically added as I explained during transaction construction. So this algorithm automatically found this UTXO in the wallet and added it as input in order to cover the fees. And it also automatically created this change output of 990. So of the 1000, 10 are fees and 990 are changed. So this all happens automatically. All we specified in our constraints was that we want to forge the token with amount 444. And this is something now we haven't seen before. This is now a transaction that actually forges native tokens. So this is the currency symbol, and we saw that earlier when I, in the REPL, tried out what our currency symbol actually was. So this is the hash of our policy script. And this is the token name, and that just comes from what I entered in the endpoint, in the parameters, in the simulation tab, the ABC and the amount. And we see that we have a second output to wallet 2 that contains this token, this newly minted token. Actually, these two could be combined in the same output because values can be combined. So there's not really a need to have two separate outputs. I don't know why the algorithm does that. Maybe it's a little bug, but it's not wrong, of course. It might just be a bit more expensive, this transaction, because it's bigger. But in any case, it's correct. So we get the change and we get the tokens paid into the wallet, the newly minted tokens. And again, all I specified for the transaction was that it must contain this forge field. And then the algorithm, the balancing algorithm, automatically figured out that we need this input to cover the fees, and then the change output and an output where the minted tokens actually go. So now if we look at the one for wallet 1, it's exactly the same, just with wallet 1. And in particular, we see it's exactly the same token. I mean, same monetary policy and also the same token name, because in the simulator tab we chose the same token name. We could have chosen a different one, of course. Then we would have created a different asset class with a different token name. And finally, let's look at the burn transaction. So again, we have a forge field, and now again with the same currency symbol and token name, but now the amount is negative. And now the algorithm that constructed the transaction did something slightly different, because it sees, okay, in order to burn 222 of these tokens, I must have an input of these tokens. So, and the only available input that has these tokens is this one with the 555 that we minted earlier. So here are two inputs to the transaction. The ADA input to cover the transaction fees, and then the token input. And in this case, actually the algorithm did combine the change outputs into one transaction. So we have the fees and we have one change output that contains the ADA change, what is left over after paying the fees. And it also contains the token change, what is left over from the 555 after burning 222. And the end result is, we see here, so both wallets have 980, and wallet 1 is left with 333 tokens and wallet 2 with 444. So we see that indeed with this currency symbol and the corresponding policy that we wrote, which allows all burning and all minting, we can do arbitrary things. So arbitrary wallets can mint as many tokens with arbitrary token names as they want, and they can freely burn. So this is probably not a very useful monetary policy, because the point of having a token is that it represents some sort of value. So if anybody at any time can mint new tokens, this token won't really make much sense. There might be some exotic use cases for it, but it's probably not very common that you would use this currency symbol for anything, for any real application. Finally, I also want to show how we can test this using the emulator trace monad I explained last time without using the playground. So I write a test function in I/O that uses this run emulator trace I/O, and now this do block is in the emulator trace monad. So I just define tn to be the token name I always use, this ABC. Then I activate the contract, the endpoints contract for both wallets 1 and 2, and get handles H1 and H2. And then I do exactly what I did in the simulator. So I call the mint endpoint on wallet 1 with these parameters. So wallet 1 mints 555 of this token. Then I call the mint endpoint on the wallet 2, 444 of this token. Then I wait for one slot, and then I call the mint endpoint for wallet 1 again, but now with a negative amount, and again I wait for one slot. I can try this out in the REPL. So if I run test, then we get the same that we got in the playground now in the console. It's not as pretty, but of course the advantage is that we don't have to start the playground. So the development cycle is much faster. So we see the log messages. In particular, we see the three logs that come from our contract where we forged the value. So here we have the 555, the 444, and finally the minus 222. And we see the final balances. So we see that wallet 1 has so many Loveless left, and here, so this is in this flattened display. So this is currency symbol and token name. So in the case of Loveless, it's empty string, and here we have our currency symbol again and our token name ABC. So wallet 1 has 333 and wallet 2 has 444 and has 10 Loveless more because wallet 2 only did one transaction, one minting transaction, only had to pay transaction fees once, whereas wallet 1 had 2 transactions and had to pay fee twice. So this was a full walk through for a very simple policy script. A policy script that allows arbitrary minting and burning of tokens. Let's look at a more realistic example next. So I made a copy of the free module called it signed, and now want to modify this first example to a more realistic example. And the probably easiest realistic minting policy is one where minting and burning of the currency in question is restricted to transactions that are signed by a specific public key hash. So that is similar to a central bank in like fiat currencies. If you look at the US dollar or the euro or the yen, then not every person in the world can freely mint US dollars, for example, but the US government or the central bank of the United States can do that. So in that sense, this is like a central banking policy where one party has the right to create new items of the currency or burn existing ones. So that means our policy is no longer without parameter. We need a parameter. We need this public key hash that has the right to mint and burn. So let's add that here. Turn that into a parameterized policy. Now we will actually have to look at the context. So as before, given the context, we can get the txinfo with the function script context txinfo. And now we know that this txinfo has the list of all signatories of the transaction. And when we had an example with signatories before, I just used the elements function to check that the given public key hash is an element of that list. However, there is a more convenient function in the ledger module that's called tx-signed-by. So if I'm in the REPL and I import ledger, then I can look up the signature of tx-signed-by. So that takes a txinfo and a pub key hash and returns a bool if this txinfo, the transaction corresponding to the txinfo, has been signed by the public key hash. So we can use this. So tx signed by. So the first argument is the txinfo, which we already have, and now just the signature we expect, and that's the pkh argument. So this changes the logic and makes it more realistic. So now the policy is parameterized by this public key hash, and the policy says that whenever a transaction tries to mint or burn this currency, then that transaction has to be signed by the given public key hash. Now, as before, in order to get the script, because this is now also parameterized, so there we also have a pkh. This wouldn't be type correct anymore. And as before, we can't simply apply the pkh argument here because pkh is only known at runtime and not at compile time. And this template Haskell quote only works at compile time. And we can do exactly the same that we did before using apply code and the lift class. So Let's rewrite this. Let's turn this into a function, the script of a function, Pluto's core function, that takes a lifted public key hash. So I can first write it like this. So given a public key hash, let's call it pkh prime, I apply my function make policy to pkh prime, and then wrap that typed function as an untyped one in this low-level representation. And now, of course, so this is now a Pluto's core script that expects a lifted public key hash. So as before, I can use the Pluto's TX apply code to actually apply this script. And also as before, I can use Pluto's TX lift code pkh. And I don't need the parentheses. And now I get a warning here because I can do eta reduction. So instead of doing this, I can simply compose the web monitoring policy function with the make policy function. So this is exactly the same that we did for validation scripts when we wanted parameterized validation scripts. Okay, now some further modifications. So currency symbol now also depends on the pub key hash argument. It's also parameterized. So here I can just compose. It's the same as here. I could write, I could give this argument here and then write it like this. But then I would get the same warning that I can write that simpler using function composition. So let's do that. Now for the off-chain code. There I actually don't have to change my parameters because a wallet that wants to mint or burn the currency can only sign with its own public key hash because that's the only signature the wallet can provide. So, and the wallet has the capability to look that up for itself, so we don't have to extend the parameters. So we can leave that as is. Maybe just rename free schema to signed schema. And here as well. Okay, and now, of course, here for currency symbol, this is now no longer a constant. It's a function that takes a public key hash, similar for policy. So we must get the public key. And that is another capability that this schema via the blockchain actions offered. So we said before, this blockchain actions all the capabilities to interact with the blockchain. So one example is submitting transactions. And another example is looking up the wallet's own public key. So can do it like this. So public key is, and the function is called own pub key. But there are actually two versions as we see here. So that's not the one I want. I want this one. So that gives me a contract whose result is pub key. So in order to disambiguate between the two, I qualify that with contract. Okay, so now I have the PK, and now I can get the hash by simply applying the pub key hash function to that. So pub key hash PK. So this is now my own public key hash. Actually, I can write that shorter using the fact that contract is a monad and hence a functor. And remember, we have fmap for functors. So if you have a functor f, like contract or IO or any other monad or lists, and a function from A to B, then we can turn FA into an FB. So I said the standard example for fmap is the map on lists, if f is the list functor. So if you have a list of a's and a function from a to b, you get a list of b's by applying that given function to each element in the list. And you can do the same for all functors, and in particular for all monads. So if f is contract, it tells us if we have something of type contract A and a function from A to B, we can turn it into something of type contract B. And we can apply this now for FA own pub key, which is of type contract pub key. And as function, we use pub key hash, which turns a pub key into a pub key hash. So then fmap of that function will turn contract pub key into contract pub key hash. So we can write that simpler by getting immediately pub key hash and using fmap pub key hash contract on pub key. So I don't need this line after all. And I would normally write that even shorter, because for fmap there's also an operator that's the same. It's just not a word. It's an operator. So that's even shorter. And that operator is this dollar in angle brackets. So this is now equivalent to what using fmap. Right, so I have my own public key hash, and this is what I need to actually determine the currency symbol. So our currency symbol corresponding now to the wallet's own public key hash. So the other two arguments should still be fine. For policy is also now parameterized, so I also have to apply the wallet's own public key hash to that. This line should still be fine. So should that and that and that. So that should all be good. And here I just have to rename it to signed schema. Let's see here as well. And our trace, I think that should all still be valid. So let's try it out. Okay, it seems to work. It looks very similar to before, but where before we had one currency and every wallet could mint or burn that one currency, now the currency is parameterized by this public key hash. So that means if two different wallets use this contract, they will end up with different currencies. And we see here that so wallet 1 is again minting, but we see the currency symbol is now different to what it was before, because the code is different, the policy code is different, so the hash is different. And we also see that for the minting of wallet 1 and wallet 2, we get two different asset classes, two different tokens. So the token name is the same, ABC, but we have completely different currencies. So now wallet 1 can only mint or burn this currency, and wallet 2 can only mint or burn that currency. And okay, here in this line, wallet 1 burns some of the tokens it minted earlier. And then when we look at the final balances, we again see that wallet 1 and wallet 2 each have native tokens, but now it's not the same anymore. It's given by different monetary policies. This token can only be created and destroyed by wallet 1, and this token can only be created and destroyed by wallet 2. Let's talk about NFTs next, non-fungible tokens. That is, tokens that can only exist once, where there's only one coin in existence. The examples of native tokens that we have studied so far are definitely not NFTs, because we could easily mint as many as we wanted of those. Both in the first example, where minting was totally uncontrolled, but also in the second. As long as you are the owner of the specified public key hash, you can mint as many tokens as you like. Now, in order to produce an NFT, maybe the first naive idea would be to actually, in the policy, look at the forge field, which we haven't done so far. All we did look at in the last example was the signatories of the transaction. But if we actually look at the forge field, we could add a condition to the policy that the forged value has an amount of 1. But that wouldn't help us. That would only mean that during one transaction you can only mint one token. But nobody could stop us from submitting as many of these transactions as we like, and then again mint arbitrarily many tokens. So that won't do. That won't enable us to guarantee that a given token can only exist once. A second option that is actually being used already on the Cardano blockchain, because native tokens are available since Mary, which predates Plutus, is to use deadlines. So we saw in previous examples, in previous lectures, how time can be incorporated into Plutus script. And we can do the same, of course, in policy scripts. So the idea here would be to have a deadline that only allows minting before the deadline has passed. Then if you want to do an NFT, you mint one coin before the deadline has passed and then allow the deadline to pass. And then it's guaranteed that after the deadline, no new tokens will ever be minted. But in order to check that before the deadline you only minted one, you need something like a blockchain explorer. You must check on the blockchain that only one of these tokens was ever minted before the deadline. You're guaranteed that after the deadline, no new ones can be minted, but in order to make sure that only one was minted before the deadline, you actually have to check with the blockchain explorer. So in that sense, the NFTs that are on Cardano right now are not true NFTs in the sense that the currency symbol by itself guarantees that they are NFTs. In order to check that only one exists, you have to look on the blockchain. Now, using Plutus, it's actually possible to mint true NFTs, where if you know the policy script that corresponds to the currency symbol, you can be sure that only one such coin can be in existence without having to resort to something like a blockchain explorer. And if you think about how to do that, you must prevent from there ever being more than one minting transaction for the token in question. So whatever you write in your policy script, it must only result in true for one transaction. And it must be impossible to do the same again in another transaction. And at first that sounds impossible, because why can't you simply do the same transaction again later, and then validation should again succeed, and it should be possible to mint token again. At least if you do it in the same slot. I mean, we mentioned deadlines before, so of course time plays a role. But why can't you simply at one slot issue the same transaction several times? And the key here is that we need something that's unique. We need something on the Cardano blockchain that we can refer to in our minting policy that is unique, that can only exist in one transaction and never again. And that is a very important trick, something to keep in mind. And the idea is to use UTXOs, because for the reason how UTXO works, UTXOs can only exist once. Every UTXO is unique. You can never have the same UTXO again. A UTXO is there, and at some point it may be consumed as input to a transaction, and there can never ever be the same UTXO again later in the life of the blockchain. Of course, there could be another UTXO that goes to the same address and has the same value and has the same datum, but that will still not be the same UTXO in the sense it will have a different ID. So what is the ID of a UTXO? Well, a UTXO is the output of a transaction. So in order to pinpoint a specific UTXO, you must pinpoint the transaction it came from via its transaction ID, and you must say which output of that transaction it was. The outputs of a transaction are ordered, so by specifying the transaction that produced it and saying which item it was in the list of outputs, you can uniquely identify an UTXO. And transactions are unique. There can never be the same transaction again. And because transaction and index determine the UTXO, this implies that UTXOs are also unique. So now, of course, you can ask, why are transactions unique? And that is a bit subtle, because they wouldn't be unique necessarily if it wasn't for fees. If it wasn't for fees, you could have a transaction that has 0 inputs and only outputs without value. So transactions with no inputs and outputs where each output doesn't have a value. Such a transaction could exist several times. You could have the exact same transaction and it would have the exact same hash and hence the exact same transaction ID. But in a system with fees like Cardano, you can't have such a transaction because you always need an input that provides the fees to pay the transaction fees for the transaction. And as soon as you have an input, that input must come from somewhere. It must come from a previous UTXO. So basically, by a simple induction argument, you see that as soon as you have fees, transactions can never be repeated. You can never have two identical transactions in the sense that they have the same transaction ID, because they must spend fees, and these fees, because double spending is impossible, must be different UTXOs for different transactions, and the inputs are incorporated into the transaction hash. So if you have two transactions with different inputs, those two transactions also will have different transaction IDs. So that means that every transaction in the history of the blockchain is unique, has a unique ID, and that implies that also every UTXO in the blockchain has a different ID, a different combination of transaction ID and index. And this is a very important fact, and that is a fact that we can use in order to create true NFTs. So the idea here is to name a specific UTXO as parameter to our minting policy. And then in the policy, check that the transaction that does the minting consumes this specific UTXO. And because of what we just said, once a UTXO has been consumed in this transaction, it can never exist again. So there can't be another transaction that consumes the same UTXO. And this strategy guarantees that with a minting policy like that, there can only ever be one transaction that consumes this UTXO. And that is what we want to achieve in order to guarantee that we have a true NFT that can only be minted once. I created a copy of the previous module, the signed module, called it NFT. And now let's turn the signed policy into a true NFT policy. So the idea is to not use the pub key hash of the central bank anymore as parameter to the policy, but instead a UTXO, which leads to the question, what type corresponds to a UTXO? If we look in the REPL and if we import Ledger again and remind ourselves what TF-info was, then so far we've only ever looked at these generic fields that are part of the transaction itself and not of the inputs and outputs to the transaction. But if we look at the inputs, we see that there's a list of something of type called txin-info. And if we drill into that, we see that it's a record with two fields, and the first is called txin-info outref, and it's of type txoutref. And this is as the name suggests, it references a transaction output. So in other words, it's an identifier for an UTXO. So that's exactly what we need. So let's replace this by tx out ref. And then we should rename it to something like oref maybe. The logic here, of course, is no longer valid, but we can save this expression because we will need the tx info. So let's give that a name, info, type tx info, info equals script context info of our context. Okay, now we are ready to write the logic. So we must check that the transaction that is doing the minting contains the specified UTXO as input. So let's delegate that to a helper function. Let's call it something like has UTXO, and then we can do trace if false and say UTXO not consumed. If it fails, has UTXO type bool. Okay. And how do we do that? Well, the inputs we saw, there's the field txin for inputs. It takes the tx info and gives us a list of txin infos. So we have the info, we just give it a name, info. So this is now the list of all inputs. And we must check that one of those references our oref, the UTXO we use as a parameter. Now in Haskell there is a function, a very useful function called any. This is now the version that comes from standard Haskell, but there is also an any available in the Plutus Prelude, so we can use it in scripts. And the way any works is, so we haven't talked about foldable, but you can think list here. So list is a special case of a foldable functor. So this any function gets a predicate, a function from A to Boolean, and then let's say list of A's, and returns true or false. And it returns true if any A in this list satisfies the predicate. So for example, we could do any even, and now a list of ints, 2, 3, 5, 7, and that will return true. And that means is there any element of this list that is even? So if I remove the 2 or change it to a 1, I will get false. So we can use that. So we just need the right condition. Any, now we need some condition that checks all the inputs, and we apply this to the list of all inputs. So now, given an input, when are we happy with it? Recall the tx, what we saw before, info, tx in info. So given an input, that is now what we have there, we can check that the tx in info outref, of that input is the right one, the one we expect. So tx in info outref I equals the oref, the parameter to our policy. So for a given input, this lambda expression checks whether the UTXO that's referenced by the input equals the one we are expecting. And the any checks this for all inputs. And if we find one that consumes this UTXO, then this will return true. And if this UTXO is not consumed, then it will return false and the policy will fail. So are we done? Well, right now we have a policy that guarantees that only once can minting or burning happen for this currency symbol. So we have created a currency symbol that can only be used in one single transaction for minting or burning. But of course, in that single transaction, right now, the way the policy is written now, we could do whatever we like. We could mint 1,000 coins, or we could mint of several different token names for this currency symbol. So now it really depends on what exactly we want. I mean, there are different possible use cases. So for example, maybe we really just want one single coin for one specific token name. Alternatively, maybe we want a currency symbol that allows us to mint several different NFTs in one go. Maybe we have a series and different token names, and for each token name, we want to create an NFT with this currency symbol. So this is now really up to us what we want. So let's say we go with the first option, that we just want to mint a single coin for one specific token name. So in that case, it probably makes sense to add a second parameter, the token name that we want. And we must give it a name, let's say TN for token name. And we need now a second condition that checks that we really just forge or mint this one specific coin. So the currency symbol we have defined here with this policy, this token name given by the parameter, and the value, the amount, should be 1. So we must add a second condition, and that ensures that the forge field is correct. So let's pick an error message in case this is not satisfied. Something like wrong amount minted, and check minted, minted amount. Something like this. And let's define this here. Check minted amount of type Boolean. Now, how do we implement this? We want to check that this transaction, the only coin that is forged is the one with the currency symbol we are just defining by this policy, the given token name, and then the amount should be 1, just one coin. So we can, first of all, we need access to the forged value. And in the REPL, we can check if we ask for information about the txinfo type. Again, there's this field called txinfo forge. So by using txinfo forge, applying it to our info, so this is now the value that is forged. So how do we check that that equals exactly one coin with the given currency symbol and the given token name? Well, there are several options. We could, for example, use this flatten value function that I demonstrated earlier, which converts this map of maps that the value is into this flattened list. So a list of triples, currency symbol, token name, amount. So we want this map to be equal to the list with just one argument, with the currency symbol, the token name, which is given by this parameter tn, and amount 1. We want one coin to be minted. So now we have one problem left. What is the currency symbol? And the problem is the currency symbol is given by the hash of the compiled script that we get by compiling this function that we are currently implementing. So that sounds as if we have a problem there, a chicken and egg problem, because we need to write the right value here. But in order to get this value, you first need to write this function, complete writing the function in order to compile it and get the hash. So somehow it seems difficult to know the hash at this point, the correct currency symbol, because that's the one we are just busy defining. But luckily there's a function called ownCurrencySymbol, which is meant for exactly this purpose. So ownCurrencySymbol, if you are in a function, and that takes as argument the context. So if we are in the process of writing a minting policy, then by using the function ownCurrencySymbol that takes the script context, we get access to the currency symbol we are in the process of defining. Right, so this should do it. We grab the forged value from the info, flatten it into a list of triples consisting of currency symbol, token name, and amount. And we want that exactly one coin of the currency symbol we are just defining, the token name we specified, and one. So one coin is forged. And this should complete it. Now we can change the rest accordingly. So first of all, policy now also takes these two parameters that we have, the txoutref and the token name. So let's add those here. Let's call it again oref and tn. So now we have a function with two parameters. So earlier I could avoid the lambda expression here by using function composition. Now with two arguments, that's not easily possible. So let's just write it explicitly. So given oref prime and token name prime, I have to wrap the result of applying make policy to those two arguments. And now I must provide them. So I must use apply code twice. I must lift the oref and the result I must apply to the lifted token name. Now let's go on to the currency symbol. Same thing. I have two parameters now, txoutref and token name, oref and tn. And again, now it's easier to do it explicitly. That completes the on-chain part, and now I need a wallet contract that actually creates a forging transaction that will then pass validation of this minting policy. And let's first think of what the parameters to that endpoint should be to this contract. And in order to get our currency symbol, we need these two parameters, the txoutref, the UTXO we are going to use, and the token name. Now the UTXO can be looked up by the wallet itself. So we have to use a UTXO that's under our own control, that belongs to us. Because when we create this transaction, in order to pass the policy, the transaction has to consume that UTXO as input. So we must be able to create a transaction that consumes that UTXO. So the easiest or the only way really is to use a UTXO that belongs to us. And the wallet can look up our own UTXOs. So we don't have to pass that in as a parameter, we can look that up automatically. So all we really need is the token name. And because we only need a token name, we don't need a special data type, so we can delete this. And the endpoint, well, we can still call it mint, but now the parameter is just a token name. And let's call it NFT schema. Okay, so this is now token name and NFT schema. Let's call the parameter tn. Right. So in order to get the UTXO, we must look up our UTXOs, the ones that belong to us. If we switch to the REPL and if we import module Plutus contract, then we have something called UTXO add. So it's a bit intimidating, but this first part basically only means that we need access to the blockchain actions that we have. So UTXO add is part of that. So let's ignore these complicated looking constraints. And what this says is, given an address, it produces a contract action. and the result is a UTXO map. So the idea is, given an address, it looks up all the UTXOs at that address. So what is an address map? Address map, UTXO map. This is just a type synonym for a map, a standard Haskell map, where the keys are TX-out refs. That's exactly what we're looking for. And the values are TX-out TXs. So the strategy is to call this UTXO add with our own wallet address. And then we get such a map back. And the keys of that map are exactly the UTXOs that belong to us. And it doesn't mean which of those we pick. As long as we own at least one UTXO, we're good. So the first step in order to do that is we must find out our own address. We know how to find out our own public key. We've done that before when we needed our own public key hash. So what's an address? We can ask for that as well. And so that's relatively complicated, and we won't use that directly, but instead we can use something called a function called pubKeyAddress. That's exactly what we need. It turns a pub key into an address. So let's do this. So now we don't need the public key hash, we need the actual public key. So we can remove this fmap. So pk is now our own public key. And now we can apply this pubKeyAddress function to our public key. So this is now our address. And we can use UTXO add of this to get all the UTXOs that we own. So UTXOs. And that is now a map. But actually, we are only interested in the keys of that map. So we must import data.map. And normally, because there are a lot of conflicts in the names in data.map with names from the prelude, standard Haskell convention is to always import that qualified. So let's import that with the qualification map. Okay, so we have this. So this is now a contract that gives us this address map, but we're only interested in the keys, so we can fmap the map keys function over this, and this will give us all the UTXOs. So again, this is this fmap. So if I didn't have that, the result would be an address map. But I'm not really interested in the values, only in the keys, because the keys are exactly the UTXOs, the TX-out refs that I'm looking for. So I fmap map keys over it, which is a standard Haskell function in the container package that to a given map gives me the list of keys. So UTXOs is now the list of all the UTXOs that this wallet owns. And I need one. Doesn't matter which one. But if there is none, if I don't own anything, I can't mint a token. So we can just make a case distinction. So if this is the empty list, we are done. We can't mint a token. So we could throw an exception, but let's just log an error, for example, and not throw an exception. That's up to us. I could just as well use throw error here, but let's just use log error string no UTXO found, something like that. Okay, and if there is at least one, so in that case we have a head of the list and then some tail, and we can just take the first UTXO we find and continue with this. Okay, so now we have our UTXO, or actually probably I should call it OREF because that's what I quoted earlier. Let's call it OREF. And maybe here those I should call OREFs just to be consistent. Okay, so now I can follow the previous contract. So what's the value we want to forge? So now the currency symbol now I have both parameters for that. So I need the txoutref, which I now have. That's oref, and I need the token name, which was a parameter to this contract. The token name is just the token name, and the amount is 1. I want to mint exactly 1 coin. Okay, now for the lookup here, the policy takes the same two parameters. So I should just provide them. Okay, and this is good, but now I need an additional constraint because I now need to consume this UTXO, because otherwise the transaction won't validate. So it's not enough that I specify that this transaction must forge that value. It must consume the UTXO I've found. That's exactly the point, how the whole mechanism works, that we insist on consuming this specific UTXO. And after we have done that, it's gone, so we can never do the same again. So we must add a second constraint that specifies that this specific UTXO given by oref is consumed. And if we check in the REPL and if we import ledger.constraints module, then we see that there is must spend pub key output. And the type of must spend pub key output is given a txoutref, it creates a constraint. So that's exactly what we need. So we must specify that it must spend the pub key output given by the txoutref, the oref we found. So now we need a second constraint. So how do we combine constraints? Well, constraints don't form a monoid, but they do form a semigroup. And the difference between monoid and semigroup is just that in monoid we have the neutral element, this memty, and in semigroup we don't. So we can still combine elements with this operator. So constraints must spend pub key output oref. Now we saw earlier that for some constraints we need corresponding lookups that allow the constraint solver to get the necessary information to satisfy the constraint. So we saw that in the case of must forge value, because this value involves this monetary policy. In the lookups we must provide the monetary policy so that that can be found. Similar, if we use a constraint must spend pub key output with a oref, we must provide a lookup that gives access to the UTXOs where this oref can be found. We can look that up in the REPL, so it's called unspent outputs, the corresponding lookup. And as an argument, it takes exactly such an address map, such a map from txoutref to txouttx, the same type that we got as a result of UTXO add. Which means I shouldn't have done it like this because I only kept the keys, but I throw away the values. But now for the lookup, I need that. So I should refactor this and give it a name like UTXOs and not do this fmap. And then I can just define the oref separately, simply as equals map keys UTXOs. Okay. Actually, I could inline that. I don't even need the orefs. So like this. I don't need this line. Okay, and now lookups I can also combine with this operator. So that's now constraints, unspent outputs, and now I can use the UTXOs because I know this oref is contained, is a key in this map. So this should then be found. Okay, this can stay the same. This can also stay the same. Now, in principle, this can also stay the same. Good, now for the endpoints, I changed the name. So that's now NFT schema. The rest is the same. Here's also NFT schema. Okay, and now in the script, okay, let's again use this. And let's try it for wallet 1 and 2. Now, of course, the parameters are different. Now I don't have these min parameters anymore. I just have the token name. So I can just do tn. Don't specify amount anymore. Here I can use the same token name. I could, of course, use a different one. And burning no longer makes sense and wouldn't be possible. So I can delete this. Right, and now I run into a problem that the semi-group operation I use to combine constraints and lookups is in the actual Haskell prelude, not in the Plutus TX prelude. So here in the imports, I hide the Plutus TX stuff, the semi-group operation, but now I must explicitly import the standard Haskell prelude with this semi-group. So prelude semi-group. Oh, that is just a bracketing error because I have this dollar here. So now the precedence is wrong. I must move the dollar and use explicit parentheses. Okay, another problem that I now run into, it seems equality of triples, which is defined in the Haskell prelude, is not defined in the Plutus prelude. So I can easily work around that. I must just do it explicitly. So let's say, so a pattern match against this list. And if I get a list with just one element, one triple, let's say currency symbol, token name, prime, and amount, then I must check that the currency symbol equals the own currency symbol and the token name equals the token name I want and the amount is 1. In all other cases, so if I don't just have one triple but 0 or more triple, I fail. Now everything compiles and I can test it. And I end up with real proper NFTs. And the two wallets result in different ones. So now this is a proper NFT. So wallet 1 and wallet 2 have both minted proper NFTs. And nobody will be able to mint something with this currency symbol ever again. So there can only be exactly this one coin. Same for wallet 2. So just as a recap, the idea with NFTs, the idea to enforce that only one transaction can mint is to use a UTXO as input, to insist in the policy, in the minting policy, that the minting transaction uses a specific UTXO as input. And because UTXOs can never exist again, once they have been consumed, the same UTXO will never exist again. This will guarantee that such a transaction can only happen once. And if in addition we enforce that in this transaction that can only happen once, a value of exactly one coin is minted, then we get a policy that guarantees that we have a proper NFT, where there's only one coin in existence. For homework, first I want you to modify the signed minting policy by adding a second parameter of type slot that represents a deadline. So the new logic should be that this pub key hash must have signed and the minting must happen before the deadline or up to the deadline. And by doing that, you basically reproduce what Mary can do. I mean, Mary can do slightly more sophisticated things because it can also have like several pub key hashes, require um, more than one signature and combine different policies with logical AND and OR. But in principle, by doing this, you could do Mary style NFTs. So add the second parameter, and then you have to modify the policy and currency symbol functions accordingly. Then for the mint parameters, we need the deadline as an additional parameter. So I added it here, and I already implemented the wallet code for this. So what I did now was I asked for the current slot. So current slot is another of these blockchain actions that you can do in the contract monad if blockchain actions are included in your schema. And then I just check whether we are already past the deadline, in which case I just log an error message. And if not, then I construct the transaction. And the only difference is now, in addition to this forge constraint, I also have a must validate in constraint where I use as interval, as slot interval, I use to deadline. So that should be good because the current slot is not after the deadline, so the current slot should be included in this. And the rest is as before. And the emulator trace script is slightly different. I'm only using one wallet, only wallet 1. And now I have this deadline of slot 10. And I immediately try to mint 555 coins. And then I wait 15 slots. So now the deadline should pass. And then try to mint again. And what we should see when we run it is that the first succeeds and the second fails. If we try this in the REPL, we see here the first log that the value was forged, and then at the second try we get this deadline passed error message, which comes here from the wallet code. So it doesn't even try to submit the transaction. If you want to test your solution that you do here for the policy, then you might want to modify this code to remove this check here to see what happens if you try to submit anyway, even though the interval has passed, the slot has passed, the deadline has passed. As a second homework, I want you to simplify the NFT policy and off-chain code. So remember, we had two parameters. We had the UTXO that needs to be consumed by the minting transaction and the token name. And now I want to drop this token name argument and always use a fixed token name, the empty byte string. So everything becomes simpler, and I want you to modify everything accordingly. For example, in the off-chain code, now we only had the token name as parameter, so we don't need that anymore because we use this fixed token name, so we can just use a unit parameter. And that means that the mint contract doesn't need any parameters anymore. So for the endpoint, I left that in, so we just have the unit. So in the simulator, that would just be a button, but you don't have to enter any values. And as test script, I kept the old one, but now instead of the token names that we had before, I just pass in unit. If we test this in the REPL, then everything works. So we forge these two NFTs, wallet 1 forges one and wallet 2 forges one. And we see they have different currency symbols because the two wallets consume different UTXOs. But the token name in both cases now the empty string. And here in the final balances, we see that wallet 1 and wallet 2 each have their unique NFT now.